So this is a chart that is very important. In some ways, it's like uh, I guess you could call the periodic table uh, of our UMI, and it's essentially what's going to give us. Um, it's going to give us the ability to understand the universal ladder in terms of a given eBPS or DPS. And to read it, what's important is to recognize that across here, so the central and most important space here is is this column here, this one that starts at 14 at the top and has a 0 and then goes all the way down to minus 35, right? Forget the next couple charts. Those are for other eBPSs. You'll be receiving or have received already a chart that will be like this, but just for eBPS 1. So this line here, basically the key here is the 0 point. You'll see that everything kind of hinges at the 0 point. So on the right side, nothing is there's not much information um, going up higher than 0. So sorry, lower than 0. And over here, there's not much higher. So basically, the numbers to the right of this column are all going up, and the numbers to the left are all going down. And there is a reason for that. So 0 is set to the astronomical or the solar radius of 1. So this is actually the whole thing is calibrated to the solar radius. And every every cube, so every cube, if you will, um, is one solar radius in distance, and the number is 139,000. Wait, 131,392,000 kilometers. And if we multiply that by 19, we get this number and then this number and all the way up. And so this starts to get kind of mind-bogglingly, crazily large, these numbers. So what happens here is going further to the right. So we've got solar radii, right? So it's 1. Then kilometers, there's the number in kilometers. Astronomical units. By the way, that's the distance between the Earth and the Sun. That's the average distance between the Earth and the Sun. You can see here that the Sun's radius is um, is uh, is not anywhere near the distance between the Earth and the Sun. And then but you get all the way to light years, and then you get to this place where now the numbers, so these are all that E means exponent, right? So this is like exponent plus 24, exponent minus 8. So this is indicating that these are smaller units, and this is larger units. But the ones that have all these exponents, they're outside of our ability to think. So we don't really want those numbers. We want the numbers that kind of slide up diagonally here. These are the manageable numbers. And for example, like 1, that's a that's a kind of a manageable number, right? It's the most manageable number. So if we're looking in light years, so this is 1 cube is 1,392,000 kilometers. Now, once you go, you're multiplying by 19 with each jump upwards. So you're going up 1, 2, 3 moves, and then it probably makes more sense to talk in terms of kiloparsecs. So actually, it moves very, very fast. The further up you scale, you're starting to get much larger things. Because here, look, in kiloparsecs, um, actually no, would that be right? Sorry, my bad. Astronomical units. Then you're talking about 63 astronomical units. That's a reasonable number. Um, so each cube is 63 astronomical units. So you're going to have a picture of the Earth, um, and the Earth around the sun and the distance between the Earth and the sun. It's visualizable. Um, and then if you go up further to, say, rung five, then you can see here the Milky Way galaxy, and the Milky Way galaxy will appear. So this is in kiloparsecs, so 276 kiloparsecs, but is the value of one cube here. And the Milky Way galaxy fits into this, is pretty visualizable in this. And then all the way up here to megaparsecs. So these are all extensions of each other, but the whole point is you figure out what the size of an object is or a structure, and you then figure out what rung of the ladder it would be on. So how many multiplications by 19 is it above this baseline? So if you go all the way up 14 times, that's what it takes to resolve the entire universe. And we've got a number for the entire universe, which is 28,513 megaparsecs. And lo and behold, that is a smaller number than 36,044. So it would fit in one cube here. So the bigger it gets, no human being can think in terms of the kilometers in the universe or the solar radii in the universe. That's just mind-boggling. So instead, what we do is we just keep jumping up these units of measure, and in this case, we're dealing with megaparsecs. But it just kind of scales diagonally across the chart. And what we're getting used to is we don't even have to think about this stuff. We're not really that interested in the numbers, but we do want to make sure things are in their correct position. What we want to know is how many jumps up from from the sun do we need to resolve the Milky Way galaxy in our field of vision? Um, how many? And here are some stars. Actually, this is suggested their size, right? There's some really big stars can be visualized, using bigger frames, but one or two leaps up the ladder, and then if you go 14 leaps up the ladder, then the whole universe is there. So that's how you'd handle that side. Now the other side is when you're going down the ladder. So you can see already that actually the microscopic is a bigger domain than the macroscopic, which is kind of wild to think. So from here we go down, right? And so we're dealing in astronomical units. Sorry, not astronomical, solar radii, which are approximately 139,000 1,392,000 kilometers. And you can see over here, this is meters, right? And because this is in metric, um, that you can just start adding zeros, right? So this is um, this just adds a couple zeros to this number, maybe three zeros. It's hard to tell, but so this is the thing in meters. So you wouldn't really um, want to be on. You wouldn't really want to measure the sun in meters, but this is the size of the sun in meters. And if you want to go all the way down to the Planck length, this insane number, 8.61 exponent to the 43rd, is that's that's how big the sun is in Planck units, which is nuts. We wouldn't do that. So we measure the sun in terms of solar radii, manageable number. But once we start going down, we start to get numbers that make a little bit more sense. So we're jumping down maybe 3 units. Oh yeah, you jump down actually from the solar radius. It's only one leap to get to the scale of the Earth. And the Earth's diameter, I guess, or radius is 12,756 kilometers. This you find out by looking up the numbers, and then you place the object at its appropriate scale in your mind palace, and then you forget about the numbers. So the numbers are only there to get you to place it at the right place. And after you've done that, you can forget about the numbers. That's the beauty of this chart. You don't have to memorize it. You just have to understand that once we get a number, we can place it at the right rung of the ladder. And then all we do is scale up and down to that. Because we're not trying to get exact measurements. We're not building rockets. We're building a memory palace. Um, so then you get down, so it would be at about rung 21 that you get the human. And this is an example of what I was saying before, is the previous one I did essentially by hand. Now I'm using the algorithms and it makes, or not algorithms, but like I'm using the Excel charts and the functions and stuff, and it makes it way easier to produce this stuff. But originally, I actually worked it all out using calculator and converting everything across the units. And it was really laborious. And I started from a different starting point. I started from an astronomical unit. Remember that? Well, and I found the Earth on on rung 21, and or sorry, the human on rung 21. Well, lo and behold, that's where it is. You know, when I'm starting from solar radii as well. So my conjecture is that regardless of where you start, what the basic cube is, you're going to find things on relatively the same space. So that's pretty interesting. Um, that needs more. It needs more research, of course. Um, I'm kind of trailblazing this stuff, and I'm certain that people who come after me working on this will find all sorts of things that weren't 100% correct, and they'll work with it, and this work will get more and more and more refined. I'm comfortable with that. But I was quite amazed that basically, yeah, this shows up on rung 21. And you'll see here's the number. So this number here in the center just tells you how many leaps up and how many leaps down. This one just takes it from the biggest and counts all the way down to the smallest. Um, and so there's 50 rungs in the ladder. That's how we know. And I discovered this years and years and years ago when I worked it out by hand. I tried to do it from the size of the Laniakea supercluster, and I did get 50. And then I tried it from the solar radii. Every time I try it, I get 50 rungs. So it seems like it's independent of what size you set, which is cool. Another amazing thing, I haven't really included this, is I actually built a similar chart for temporal measurements. So um, temporal and spatial measurements are actually on this, level, kind of the same thing. So there is a Planck time length, a unit of Planck time, and there is, of course, light years are as the length of time that that essentially light travels in a year. But to to start from the Planck unit of time and go up by factors of 19, it'll take 50 rungs to get to the age of the universe. So so that is another interesting corroboration that this is pretty much objective information. But it's not abstract in the same way as the eBPS is. It's not deductive. It's inductive. It's empirical. That's the difference. So, rational is purely kind of calculative, dealing with numbers that are not measurements of anything in the world. Um, but uh, but empirical measurements are measurements of physical things, and so this UMI is empirical, whereas the UKI is not really empirical. Um, it's rational. It's purely abstract. But okay, so let's move it down here. So the human scale, again, we're not measuring the human, we're not measuring the human in solar radii. I haven't even bothered. I've got the kilometers here. But this is a human body is 0.029 kilometers, or rough human scale. So what are we looking at here? Meters, right? So each cube is 29 by 29 meters. So you'd see a human being kind of in the center of it. And then, of course, boom, you scale down one, then that's about 2 meters, 2 meter by 2 meter cube. You can see that here. And then, yeah, a human being is very resolvable in this. And so usually a thing is across one or two rungs, right? Um, and then you zoom down further. So this is to so we're going to use this number here instead. Instead of leaps from the baseline, we're actually just going to talk about the unilateral. So on the unilateral rung 29, you get atoms, and they will occupy about two to four cells of that. And so we've got meters, decameters, centimeters, millimeters, micrometers, nanometers, picometers, angstroms. And so yeah, you're probably measuring atoms in angstroms, femtometers, atometers, electron radii, and the Planck length. So the Planck length is still way too small to meaningfully visualize an atom. But then you get down to quarks, and so quarks on what rung here? Yeah, so you can see a number like 4.7. That's the kind of numbers we're looking for, really manageable numbers, because it means um, each cell is 4.7 of whatever that unit. In this case, it's electron radii. So we can probably see an electron right in the middle of that cube. So what rung of the ladder? So this is yeah, 18 steps down, so rung 33. And then quarks, of course, are subatomic particles, right? So they're smaller than electrons. And so I don't think they even have really size as such, but they maybe they do. This is what I read. Um, and yeah, so this is 36 and 37. And then boom, even so, the Planck length here, this final column, is overkill. And it's only when you get to like rung 49, that's when the Planck length will resolve in the center. And you can see one Planck length, and then um, yeah, and then 50 is even like e- less than that. So this is a scale that will give us the whole universe. It's a universe-sized memory palace. And we can use it. We can use it to train our minds to go up and down. And fifty rungs is manageable, right? Um, and remember, you discover the measurement of a thing, and you figure out, okay, is it a big thing? If it's a big thing, it's going to be on the right. If it's a small thing, it's going to be on the left. And you figure out what unit you want to measure it in. So what unit is appropriate? Is it like kiloparsecs? So is it like the Laniakea supercluster? Or is it a planet? So is it, kilometers or even astronomical units? Is it like a tiny creature, like a tardigrade? That's in millimeters. Um, is it, is it a DNA structure? So that would probably be, that's molecular. So that's going to be around 24 to 25. And so we're training ourselves to know where, in terms of eBPS 1, where things fall on this universal scale ladder. So this is incredible training for both macrocosmic and microcosmic visualization. So we're going to stop the recording now and start it again with a different file.